Hello class, and welcome to today's lesson on limits. Limits is a new type of notation that's going to help us approximate values and find what values should be at as, I would say, as input is approaching a value or output's approaching a value. We'll get to that. So it's new notation and a new operator, so let's get to it. We'll start with something familiar, graphing the function of, well, everyone's favorite function, 1 over x. So give yourself a moment to draw that out, and we'll continue. Okay, so let's review how you would sketch this out. So I'm going to draw a coordinate grid really quickly, and I'm going to do in blue my values or my sketch for this. Now, I'm going to draw it out really quickly. Should look something like this, and something like that. And that's going to be your f of x equaling 1 over x. I'm going to explain these values though and give you even test values, or sorry, this sketch, and I'm going to explain how we get them. So let's talk about here. Why is this output, the y value, let's write that equal to y. Why is that output becoming 0, right? So let's do a test, okay? Some of you may remember this from a former lesson, but if you have f of, let's pick a large negative value, negative 1,000, right? That should exist somewhere along this region, right? If we have that plugged in, what do we get as an output? Well, we're going to get this equal to 1 over negative 1,000. I could rewrite that as negative 1 over 1,000, but you're going to get an output that is negative 0.001. That's going to be, if you need some help reminding yourself, this is your tenths place, hundredths place, thousandths place. Okay? So if you're dividing by 1,000, you're going to get this output. Now, if I would say that's what you get here, great. So it's something very like around here. It's not 0, but it's close. The reason why I bring up the 0 comment is because if I plug in, let's say, a much larger number, so let's say negative 1,000,000,000. I might do this for a few seconds. If I plug this in, you're going to just try that in your calculator and see what you get. Because I'm going to tell you, it's going to be approximately, in this case, actually I typed in as much as I could before I started losing interest. But I ended up getting a value that said it was approximately negative 1 E23. You might see that in your calculators as well. But what does that translate to? This is actually, if you aren't sure of this notation, E is referring to negative 1, so times 10 to the 23rd power. Okay? Oh, I should say negative. My apologies. Negative and negative. So it's 1 to the times negative 1. Sorry, there we go. Negative 1 times 10 to the negative 23rd power. So all that means is that you're this 10 is going to go in your denominator. You're dividing by that large number. But really what that comes out to is something that's very small. So this rule is that as you divide by a number, so dividing, I'll write this in green, dividing by a large number gives you a small number. So in this case here, since I'm dividing by a very large number, right? Like this is a very large number. You're going to get a very small number, but it's still negative, and that's important. So what if I were to say, let's rewrite this to say that I'm going to say now f of negative infinity, right, is going to go into 1 over x. So we have 1 over negative infinity. And remember, to remind ourselves, the concept of infinity is that it's a very, very large number, the largest number. Well, I say number, but it's a concept. It's not actually a number. It's just whatever infinity is, there's something beyond it. It's just something always larger. That is that idea, something larger there. And it's negative. So as we're going all the way down that number line, we're getting negative infinity. Well, if we're going to have something that's very large into just this number 1 here, right, we're going to get an output that's approximately 0. Now, remember, this is a very integral that this was negative infinity. It's not exactly 0, but it's close to 0. So we say that it's 0, but on the negative side. So that output's going to be somewhere around here, right? Oh, sorry, here, but over that side. It's going to be the negative region of the y-axis, right? So I'll do this in this color, right? That region, focusing on being close to this number line. So that output is going to be 0 with a negative little hat on top of it. So let's zoom in and say that that is our answer for this one, okay? So we're going to go over a few more cases, right? We're going to say, now if I plug in f of infinity, right, equals 1 over x, you're going to get 1 over positive infinity, right? Well, again, it's by a large number, but now we're on the other side of the axis, right? We're going over here, and we're going to get approximately a low value, but it's in the positive region, so that's going to give us a approximately 0 with a positive hat, and that's how we denote that. Okay? Now, continuing forward, there's another way of looking at it. If I'm dividing by a large number, great, but what if I'm dividing by a small number? Well, the inverse would be true, and let's review that idea, that if I'm dividing by, we already said some small numbers, but I'm going to pick one of these, right? What if I said I'm dividing by something that's close to 0, but not exactly 0, right? So I'm going to write that as 0 plus. Well, I have 1 over 0 plus. What does that give me? Well, I'm dividing by a very small number. We can rewrite that as, and I'll put this in green, 0.000000000000000000000000. Just keep going, right? 1, well, what does that equal, right? If you type that in your calculator, see what you get. Now, I will state, again, got a little bit lazy. I just kept typing until my finger got tired. And I got 1e31, which, as we discussed in our notation, is 1 times 10 to the 31st power. And this is a very large positive number. Very, very large. Like, that is huge. So, to mention that huge number, well, we talked about what very large numbers are like. Well, we referred to those as in this concept of infinity. So if we have the infinitesimally small number, but it's not exactly 0, but it's still very small, that's a concept, right? Well, we also get a concept out of it and say this is positive infinity. So that's how you get for that one. I should box all of these since I boxed one. All right, and last but not least, we're going to do one more and say that f of 0 with a negative hat, well, that's me 1 over 0, a very small number that's negative. You're going to get the opposite, which is negative infinity. So those are our 4 cases for that. All right. So let's talk about how do limits get into play with this concept. So I have a generalized definition here for you for limits, which are used to determine a specific output as we approach a specific input. So what does that mean? Well, let's look at a new function. So this function here is g of x is equal to 3x raised to the negative 2 plus 2. So I want you to try and sketch this function out now. And just take a moment, just think if you can do it. Don't put too much time into it. Just see if you can. All right. So what you may have noted already that this is a more difficult one, possibly that you may not be used to. So I would probably rewrite this to make it something more digestible and say get rid of the negative exponent. I hate dealing with those. And say this is 1 over x squared plus 2. Right? And I pulled the 3 out because it's just multiplying that whole part. So if you actually note, there's a few key points we've been talking about already, which is this 3 is outside the parent function, so it's telling you the truth. This is going to be a vertical stretch. And here, this is a vertical shift upwards because it's also outside the parent function. And here, this is our parent function. Now we've been dealing with 1 over x, but now we have 1 over x squared. And we have to think about how this parent function looks and how these transformations affect it. I will note that this is a rational function, right? So we want to look at where this domain restriction is going to exist. And you probably already noticed it should be at where x is going to be 0. So what's handy is limits can be used for this, right? So what we can say is that the notation is a limit, so I'm going to write limit okay, as x approaches 0, right, is going to give us some value, right? Now, as x approaches 0, what should we get? Well, we're going to get this value that is approaching a very large number. Why? Because, let me just write it on the side, we're going to have 1 over 0 squared, and what is that going to be equal to? Well, you never divide by 0, right? So it's not exactly 0, but it's approaching 0. Well, we just learned about those. That is a 0 with a hat on it. So let's go approach it from the left with a negative. Now we say approaching from the left, and here, let me draw a quick coordinate grid. And say approaching from the left means the left of 0, which is your negative region. So if we have, I'm going to write this out, this is your negative side, your positive side, 0 is right on the line, so you're approaching it from the left. That's what the 0 negative hat means, okay? Can I get rid of those? Okay, let's keep moving forward. So if we have this notation, we want to actually plug it into the function, so we have to write our function out, 3, and then actually I'll put it over x squared now. I'm going to write it a different way. All the same function, plus 2, right? And so what this means is, this notation is that we're actually trying to plug in or approaching a value of 0 with a negative hat into this function. So what do we get? This is all about saying there is a limit to what output you're going to get. And if you actually do this out, so 3 over 0 with a negative hat squared plus 2, you're going to get, and I'll do it in parts, this is going to be 3 divided by a very small number, but it's going to be 0 positive now, right? Because it's 0 with negative, it's a negative squared, so it's going to get 0 positive hat plus 2. This here becomes a very large positive number. Infinity plus 2. Well, infinity plus 2 versus infinity, right? Which one's larger? It doesn't really matter. They're both a concept of infinity. So this is just going to be equal to infinity. We can simplify this out to just say infinity, positive. So the limit for this is going to be equal to infinity positive, or positive infinity, I should say. So what does that mean on our graph? It means that as we're approaching negative 0 from the left, we're going to have a very large output, positive. So I'm just going to draw an arrow. So limits are going to help us say that there is a vertical asymptote at 0. Okay, and what is it? Where is it going? Is it going positive infinity, negative infinity? All right. So let's do another one and say the limit. And now this is a shorthand of writing limit. You'll see me do this pretty often. X approaching 0 from the right. That is 0 from positive. Okay, 0 from the right is 0 positive on this side. Okay. Keep going, and this is going to be 3 over x squared plus 2. Well, what do you get? We can just simply say 3 over 0 positive hat squared plus 2. Well, if you reason this out the same way, or very similarly as we did this here, you're going to get a very large number plus 2. It's going to be infinity. Okay? So we also have here, as we're approaching from the right to 0, we're getting a very large output. Okay? So that's really good for us. That's really, really nice. Now, I'm going to look at something very specific here. I'm looking at, well, what's our restriction on the range? Is it down here, right? Is it over here? Is it like this? Like, what are these behaviors? Well, let's look at what a very large number would be plugged in. Like, as we're going all the way out in this region, right? If that coordinate grid stretched that far, what would be our output? So I'm going to now do the limit as x approaches positive infinity. I'll start from the right, I guess. Okay, positive infinity for this function. What do we get? Right? So we're going to get 3 over infinity squared. Oh my god, infinity squared? How could you do that? You could square a concept? Well, infinity squared is just infinity still, so don't worry your head about it. Okay? You're going to get infinity squared into 3. That's going to be a very small number. A very small number is 0 positive plus 2. Now, if this is a very small number, plus 2. What are we going to get out of it? I would say barely any change to 2. So actually, this comes out to being 2. So as we're approaching x towards positive infinity, we're actually getting a horizontal asymptote this way. We're not exactly hitting 2, but we're approaching it. So the limit is really here to find your asymptotes, okay, as you're approaching these great values and have an understanding for it. All right, we'll do one more. We have the last bit to say x is approaching negative infinity. So 3 over negative infinity squared plus 2. Well, what happens? The negatives cancel out, and you're still left with infinity squared under 3 plus 2. We're still going to get 0 positive plus 2, and that's going to be approximately 2 again. Notice, actually, hang on, I used a wrong vernacular here. I said approximately 2. With limits, it's actually 2, because it's finding your asymptote. So that's why I'm using equal signs rather than squigglies. Okay? Notice I use squiggly up here. So when you're applying the limit, you need an equal sign. Okay? So here we go. And we're saying that's approaching 2, and it's positive 2, so we just connect. And there you go. That's your g of x function. And limits are the method or the operator that we're using to solve that, to find those horizontal asymptotes here, right? And your vertical asymptote here. Okay? So hang on, let me just write that in. That your VA, your vertical asymptote, is equal to 0, and your horizontal asymptote is equal to 2. We'll start asking more questions on where your vertical and horizontal asymptotes are, and that's going to be, you have to utilize limits to solve for that. Alrighty, so I hope you enjoyed this lesson, and I will see you all next time. Take care.